Our next chapter is set theory and logic. So this is a pretty important field of mathematics. It gives us a language and a structure to discuss the relationship between different objects and elements. This is used a lot in computer science. This is used a lot in probability. So this first lesson will largely be about terminology. So let's get started. So first, what is a set? So when we talk about a set, it's a collection of objects. They don't have to be numbers. They can be things. So for example, the set of natural numbers would be 1, 2, 3, 4, and so forth. So you can see the notation that's used here. We have a variable for the set. So in this case, it is n. And then we have the elements in the set, so 1, 2, 3, 4, and you notice here we have this ... That means that this set goes on forever, so there are more elements than we can possibly list, so 5, 6, 7, 8, and so forth. So we call this an infinite set. So it means there's an infinite amount of elements in it. The second example I have, so we have the set of 3-bit RGB colors. So you can see those 8 colors on the left. So this is something that was used in early computers. I have them listed down below. So again, we have a variable, C. And then we have each of the elements in the set. In this case, it's black, blue, green, cyan, red, magenta, yellow, and white. Now, this is a finite set because it does not contain an infinite amount of things. In this case, it just contains 8 different elements. Now, as we go through and talk about the relationships between sets and some of these terminologies, I'm just going to use the Gregorian calendar as an example. This is the calendar that is used in many different parts of the world. So it has 12 different months. Each of those months have a certain number of days. And we're just going to use these months in order to help us show examples for the different set definitions that I'm about to talk about. So the first one is the universal set. And we use the universal set to talk about all of the elements that are being considered for one specific thing. It can be finite. It can be infinite. We often use this U to describe it, but it doesn't have to be described by the letter U. It can be described by any variable. So in this case, for the Gregorian calendar, the universal set of months would be January, February, March, April, May, June, July, August, September, October, November, December. So note we have this set notation. We have these curvy brackets that surround each of the different elements in the set. And each of those elements is separated by a comma. In this case, the Gregorian calendar is a finite set because it has a finite amount of elements in it. In this case, it has 12 elements. When we want to refer to the number of elements in the set, we use this notation, a lowercase n followed by a set name. So the number of elements in set U is 12. The universal set had all of these months, and among them was December, January, and February. Universal set. Note that those are all of the months that are in the universal set, not counting January, February, and December. So I've used this term element a number of times now, and when we talk about element, it's just any individual object that's from a set. So from the universal set, March is an element, December is an element. We could have named any of the months. Note that when we're talking about elements, we don't use those curvy brackets. We just list the element. Everything, a subset is a set whose elements all belong to another set. So here I've defined the set of winter months in Canada. So December, January, February. The number of winter months in Canada is 3. You'll note that there are 3 elements in this set. And if we think back to the universal set, W contains December, January, February. So W is a subset of U. So this means that all the elements in W are also in U. It turns out that U contains more than just those 3 months, but it just has to contain those 3 for W to be a subset of U. And note how this relationship goes. W is the subset, so we draw this symbol kind of in the direction where the two ends of it point towards the main set. Back to else. Let's go on to a complement now. And the definition is a little tricky. So it's all the elements of a universal set which do not belong to a specific subset. All right, what does that mean? Well, think back to the subset W, the winter months in Canada. And this was December, January, and February. So that was W. Now look at this set W prime, which contains March, April, May, June, July, August, September, October, and November. That was in the universal set, besides the 3 months that are in W. So we call that the complement. It's everything that is in the universal set other than the things that were listed in the set W. And to show that, we use this prime notation here. So W prime is the complement of W. So this is complement notation. It's everything from the universal set that was not in the set W. All right, the empty set is a set that does not have any elements in it. So, for example, the set of months with 32 days, there are no months with 32 days. So if I had to list them, I wouldn't list anything. It would look like this. You'll also see sometimes this symbol here. It's like a circle with a slash all the way through it and extending to both sides. So typically it'll look something like that. So that is the empty set. Either one of these notations are okay. A mathematician who was familiar with the empty set would recognize both of those as representations of an empty set. Disjoint sets. So two sets that do not have any elements in common. So we have the winter months in Canada, W, which were December, January, and February. We also could talk about the set S, which is the summer months in Canada, June, July, and August. And the key thing here is there's no two elements which are in common. So if we look at any element in the set W, they don't show up in the set S, and vice versa. Any elements in the set S do not show up in the set W. So there's no elements in common in between these two sets, so we call those disjoint. So that's all of our terminology. So we had sets, which is a group of objects that are distinguishable from each other. So the vowels, for example, A, E, I, O, U. That would be a set. An element would be one specific item from the set. So that could be A. This is a finite set because it has a limited number of items in it. In fact, the number of items in this finite set V is equal to 5. We just count it. The universal set is all of the elements under consideration. So if we were talking about the English alphabet, this would be A, B, C, D, etc. all the way up to the letter Z. Let me fix that bracket. And the number of elements that are in the universal set in this case, if we're looking at the English letters, there are 26 letters in the English alphabet. A subset occurs when everything in one set is also present in another set. So in this case, all of the vowels are also in the universal set. The complement is everything that is in the universal set, but not in one of its subsets. So the vowels are A, E, I, O, U. The complement would be B, C, D, F, G, H, and I could just go through, and what I'm doing is listing every letter in the English alphabet that is not a vowel, presuming that Y is not a vowel. So if we compare this to V, none of the elements in V are in V prime. That's what makes them complements of each other. And if we were just to look into account, the number of elements in V prime is 21. Last one is disjoint. Two things are disjoint when they have no elements in common. So in this particular example, V and V prime are disjoint. In fact, you will always find that a set and its complement are disjoint, that they don't have anything in common. But sets can be disjoint and not be complements. Okay, there's a lot of terminology here. And the best way to practice this terminology is to do practice problems which involve using it and identifying things that use the terminology that I have listed here. So I'm going to go through an example problem next that involves using some of the terminology of set notation.